This is the last lecture of Chapter 8, which of course, as we have talked about, concentrates on acids and bases. Before we get into today's lecture, however, let us do a quick review on what we covered in the first part of the chapter. We looked at examples of acids and bases, common examples. We discovered they are all around our environment. Just look in the kitchen, you will see lots of compounds that can be classified as acids or bases. We had a chemical definition or chemical definitions of acids and bases. One, of course, was the Arrhenius, and the other one was the Bronsted-Lowry, where an acid is a proton donor and a base is a proton acceptor. Remember that a proton here is H, hydrogen plus to be specific. Then we looked at acid-base reactions. We said that an acid-base reaction was one where an acid donates its proton to a base, and that yields the product. We had a new term, conjugate acids and bases, and we defined a conjugate base as an acid that has lost its proton. So if you have an acid HA, for example, if it gives up its proton H to become A minus, that's the conjugate base. Then we looked at the relationship between conjugate acids and bases. The primary take-home lesson here is that a strong acid, HA strong acid, will result in a weak conjugate base. So after HA has given up its proton H, the conjugate base, A minus, is a weak base. Then we looked at the relative strengths of acid and bases, and we did that primarily by looking at a table to tell us which is a strong acid and which is a weak acid. In today's lecture, we'll do some calculations to determine strong acids and strong bases. For today's lecture, what we look at is acid-base equilibrium and the constants. So we'll learn how to calculate here the equilibrium constants for strong and weak acids, primarily weak acids. We'll introduce a new term, pH, and we'll examine how to calculate the pH of different solutions. Another term that we'll introduce is titration. Titration here is a method to determine the concentration of an unknown acid or base. So it's just a process that's used in the lab to determine the concentration of an unknown acid and base, and we'll conclude by looking at buffers. Let us start our discussion on equilibrium constants. So imagine a weak acid, HA. Notice it's an acid because it has here H. So it's an acid, Bronsted acid. If it's dissolved in water, as you can imagine, an equilibrium will be established because it's a weak acid. So in water, what you'd expect to find would be all four species. The unreacted acid, or some of it, water, of course, and its conjugate base, and of course here we have the conjugate acid. So this would be the equilibrium that's established here in water. Notice this is the acid, so it's donating its proton to water to become H3O plus, and its conjugate base is A minus. As you have seen from previous chapters, we can calculate the equilibrium constant using this expression here, where it's the product divided by the reactant, or to be more specific, it's the concentration of the products at equilibrium divided by the concentration of the reactants at equilibrium. So the numerator here has A minus, which is right here, times H3O plus, which is right here, divided by HA, which is right here. Notice that H2O is not included in this equilibrium expression. Why? Because it is the solvent and its concentration is extremely large compared to HA and A minus and H3O plus. So for this equilibrium constant, it's a little different, and it's called Ka because it's the acidity of an acid in water. So that's why H2O is not included here. So this expression here is the equilibrium constant for the acidity of a weak acid. Let us apply that and look at another concept here. So for acetic acid, as we have discussed, is a weak acid. Its equilibrium constant Ka is 1.8 times 10 to the negative 5. Notice negative. So it's a small number. In chemistry, we tend not to work and write small numbers, but instead we relate it to something else. Here we can express that same small number as pKa. So pKa here is a way of converting this small number to another number. And the expression is right here. The pKa is equal to the negative, notice, negative log of Ka. So notice this is the Ka right here. And this is a new term, pKa, which is equal to the negative log of Ka. So you'll need your calculators. So you'll plug 1.8 times 10 to the negative 5 in your calculator and take the log of that, and the negative number should be 4.75 or will be 4.75. So, conclusion. In chemistry, we will sometimes use both terms or both concepts here. Ka, which is typically a very small number, and in some cases we'll use the pKa, which is typically a number that's more manageable. So you can go from pKa, from Ka to pKa using this expression. So this is your conversion factor. So you may want to practice using that on your calculator. Let's look at a table here of Ka and pKa values. So here is acetic acid. As we have seen, the Ka here is 1.8 times 10 to the negative 5, and the pKa is 4.75. A weaker acid, weaker than acetic acid, is HCN, hydrocyanic acid. Why do we say it's weaker? Because the Ka is 10 to the negative 10. Notice this is negative 5. So 10 to the negative 10 is a smaller number, which means that HCN here is a weaker acid than acetic acid. If you convert this Ka into pKa, notice that this number is now larger than this number. So there's an inverse relationship. Let's see why we call it an inverse. Inverse, of course, means as one increases, the other one decreases. So as the Ka here increases, stronger acid, the pKa decreases, small number. here is a small number, and here is a large pKa. So that's the relationship here, which is an inverse relationship. Let us look at a specific example here. So as we point out, it's an inverse relationship. So let's look a little closer. Formic acid is a strong acid. How do we know it's a strong acid? Because Ka here is 10 to the negative 4. Even though it's negative 4, it's still relatively strong compared to boric acid, which has a Ka here of 10 to the negative 10. Negative 10. Smaller number. Doing the math, so put these numbers in your calculator, put this number in your calculator and convert it to pKa. You should get 3.75. Put this number in your calculator, 7.3 times 10 to the negative 10, and convert it to pKa using the equation pKa is equal to the negative log of Ka. You should get 9.74. Conclusion: formic acid is a stronger acid because it has a larger Ka and it has a smaller pKa. Boric acid is a weaker acid because it has a smaller Ka, but notice it has a larger pKa. So that is the inverse relationship. So you should be able to look at two acids. If given the pKa values, you should be able to tell which one is a stronger acid and which one is a weaker acid just based on the pKa values and the relative difference. Let us look at an example here. So, the Ka of lactic acid is this number, Ka. The question is, what is the pKa? So you'll have to get out your calculators here. Here's your conversion factor. pKa is equal to the negative log of Ka. So get your calculators, punch this number in, and take the negative log of it, or the log, and the negative answer will be the pKa. So pause for a second and do the math and determine which one of these values will be the pKa of acetic acid, of lactic acid, pardon me. After doing the math, you should come up with this as your answer, 3.08. So 3.08 is the pKa of this number. By the way, you should be able to take this number 3.08 and convert it back to the Ka. So again, we won't see a lot of that, but you should be able to take the antilog of this number here, and you should get back this number. So you should be able to use this equation to not only calculate pKa's, but also to calculate Ka if given the pKa. Okay, let us look at pure water. Why are we concentrating on water? Water, of course, as you know, is the solvent. It is the most common solvent that's used in not only the chemistry lab, but in just around all solutions. So water is a very common solvent. So let's examine it a little closer. We mentioned that water is amphiprotic, which means that protons here means, of course, from the definition of Bronsted, an acid is a proton donor and a base is a proton acceptor. So water can act as an acid and water can act as a base. If water here gives up its proton, it's an acid. If water accepts a proton, it becomes a base. And here are your conjugate acid, and conjugate base that results from that proton transfer. This equilibrium constant here, though, is very small, as you can imagine, because we actually ingest water, so it will not have a lot of H3O plus or OH negative present. If you write the equilibrium constant here, K, but this time we're using Kw because it's water, specific for water, Kw. You can see that the product divided by the reactant would be this. You may be asking, why didn't we divide by the equilibrium concentration of water? And the answer is because it is the solvent, so its concentration is extremely high. So we just include just the equilibrium concentration of the conjugate base and the conjugate acid, which is H3O plus and OH negative. That can be calculated or determined in the lab, and that's determined to be 1.0 times 10 to the negative 4. So this is the equilibrium concentration of water. So if you have a glass of water, you will have a very small, an extremely small concentration of H3O plus and OH negative, which is governed by this equilibrium constant here, Kw. Let us apply that. So we said that the equilibrium concentration of H3O plus and OH minus is, or the product is 10 to the negative 14, which means that the equilibrium concentration of H3O plus is 10 to the negative 7 moles per liter in pure water. Let's introduce another concept here, and that is the concept of pH. pH is equal to the negative log of H3O plus, or of protons, H plus. But since it's done in water, it's typically written as H3O plus, the hydronium ion. So this is a new equation for us. pH is equal to the negative log, notice again, negative log of H3O plus concentration, or the equilibrium concentration. Converting this H3O plus to pH means that the pH of pure water is 7. So you've often heard the saying that the pH of pure water in neutral is 7. That's because it's the most common solvent, and that's what it calculates to be 7 because of the low concentration of H3O plus. And using this equation for the conversion, we get the pH of H3O plus in water as 7, and that is the pH of pure water is 7. This means, however, that if you should get water as a solvent and add an acid to it, it will generate here more H3O plus, because an acid by definition donates its hydrogen here to water to form H3O plus. This H3O plus is the same H3O plus as we have discussed before. So using this expression here, we can calculate the H3O plus concentration in an acidic solution. And of course, what we'll discover is that in a neutral solution, as we've seen, the pH is 7, but one that acidic has a larger concentration of H3O plus, the pH is less than 7. Why less than 7? it gets back to this inverse relationship here for the negative log. So acidic solution with a lot of or higher concentration of H3O plus has a pH of less than 7. A basic solution which has here an H3O plus or does not have a large concentration of H3O plus is greater than 7 because again of the negative log of H3O plus. So once again, conclusion. An acidic solution has a pH less than 7. So if you measure the pH of a solution and it's 6, it's acidic. If you measure the solution of an unknown solution and the pH is greater than 7, 11 for example, that solution is considered basic. How do we measure this pH of a solution? We have here a pH meter. So a pH meter is an instrument that you just insert into a liquid here of unknown pH and just do the reading here. It will tell you the pH of that solution. So for example, this pH, the pH of this solution here is 7 because that's what's shown on the pH meter. Here are some practical examples of pH. Of course, as you know, in the battery, the liquid that's in the battery is acidic and the pH is 0.5. That's very acidic. Vinegar that we use on salad dressing is between 2.4 and 3.4. Not as acidic, but acidic because the pH is less than 7. Let's go over to this side here. So we have here ammonia that we use to clean surfaces in the kitchen. Its pH is 11.7, a lot greater than 7, so therefore that is a basic solution. So again, looking at the pH, you should be able to tell if that solution is acidic, less than 7, or basic, greater than 7. Let us turn our attention now to a concept called titration. So, if you got a job as a chemist, and your first task is to determine the acidity of a solution. What is the concentration of acid that's in an unknown solution? So here are just some examples. So vinegar, for example, if you wanted to determine the concentration of vinegar, of acetic acid in vinegar, how do you determine that? You can determine that by a process called titration, or a procedure called titration. Let's see what that looks like. So titration here is an analytical procedure to determine the concentration of an unknown solution. So here we have a known concentration that reacts with a solution to give us some information about the unknown. So let's dig a little deeper. So here's how it works. So we have here HCl and KOH. So we know that's an acid and this is a base. Key here is the stoichiometry. 1 mole of HCl will react with 1 mole of KOH to form products. So at the end of this reaction, 1 mole of HCl will react with 1 mole of potassium hydroxide. So if you had here 0.5 moles of HCl, it will take 0.5 moles of KOH for that reaction to be complete. So just imagine, now that you have an unknown, if you have an unknown concentration of HCl and you know that it took a specific concentration of KOH to react to completion, if it took 0.25 moles, for example, of KOH, you know that the concentration here is 0.25 because there is a 1-to-1 relationship. So if you know the concentration and number of moles of one, you can determine the concentration of the other based on this 1-to-1 reaction. Okay, let's take it a step further. So a summary here is we must know the stoichiometry, which means the reactant, the ratio of the reactant or the number of moles of reactant to give the product. The reaction must be rapid. So in other words, after you mix a acid and base, it must be completed in a fairly short time. But here's the trick. We would like to know when the reaction is complete. So when the reaction is complete, we call that the equivalence point. When the reaction is complete. So we need some way of telling that the reaction is done. And of course, we need some accurate measurements. So once again, if we have here an unknown concentration of HCl, and we have a known concentration of KOH, when the reaction is done, or when the reaction reaches an equivalence point, we know that 1 mole, conversion factor, of KOH will react with 1 mole of HCl. So therefore, if we have an unknown here, and we know concentration here, we can determine the unknown concentration. Let's see how we do that on a practical basis. So in the lab, you get your unknown acid, put it in an Erlenmeyer flask. You get your base, which you know the concentration of because you actually went in the lab and made it a specific concentration. You put it in a tube here called the burette tube. And so here's your base, known concentration. Here's your acid, unknown concentration. But we know its volume though. So you add here your base to your acid. You add your base to your acid until you get to a point that's the equivalent point. But how do you know that? You know that by putting an indicator into this solution. That indicator changes color whenever you reach that equivalence point. This indicator here is called phenolphthalein. There are quite a few others that are shown in the text, but one that's very common is phenolphthalein. So at equivalence point, the reaction is done, and you have a solution that's now turned red, which means that the reaction is complete, which means that an equal amount of moles or number of moles of base reacted with the same number of moles of acid. Okay, so let's apply that concept here to a problem. So in a titration experiment, 25 mils of an unknown acid, HCl. So we have 25 mils of that acid. We do not know the concentration. Remember again, concentration is written in moles per liter or molarity. So we do not know the molarity of that HCl solution. So what is done is we do a titration, and it takes 30 mils of 0.2 molar KOH to reach the equivalent point. Another term that's synonymous with the equivalence point is endpoint. So once again, let's just make sure we understand the question. We have an unknown solution of HCl. We do not know the concentration. We do not know the molarity. But what we have here is 25 mils of that unknown reacted with 30 mils of 0.2 molar KOH to reach equivalence point. Shown differently here is we have here the KOH, and we're saying that we have 30 mils of 0.2 molar KOH reacting with 25 mils of this unknown concentration at equivalence point. So what that means, at equivalence point, the number of moles of KOH is equal to the number of moles of HCl. Here's our conversion factor. As we have seen before, molarity, concentration, is equal to moles per volume, which is written in liters. So we need to find out the molarity of this HCl. Let's see how we do it. Number of moles of base. We know that because we have here, we can use this equation to determine the number of moles, which is 0.03 liters. Notice I'm converting my milliliters here, 30 milliliters here to liters, times its concentration. Its concentration is 0.02 moles per liter, or molarity, and this works out to be 6.0 times 10 to the negative 3 moles of KOH. So we have used up 6.0 times 10 to the negative 3 moles of KOH. That means that we also have 6.0 times 10 to the negative 3 moles of our HCl. So at the equivalence point, the number of moles of HCl is also equal to 6.0 times 10 to the negative 3. So all we need now is to calculate the concentration or the molarity. So we go back to this equation here, or this conversion factor, and of course we know the molarity is equal to moles per volume in liters. We know the moles because it's the same, and the volume is 25. By the way, this should be 25, is 0.025, and this is equal to 0.25 moles per liter, or that is the molarity of our acid. Buffers. Let us turn our attention now to buffers. A buffer is a solution that's resistant to pH change. It's resistant to pH change. Some books describe it as a shock absorber to pH change. So in other words, if you have a buffer and you add an acid to it, you'd expect, if there were no buffer, the pH to change. If you have an acid, the pH would go negative, would be small. But in a buffer, the pH would not change by much. A buffer is made by having a weak acid and its salt, or its conjugate base, mixed together in equal molarity. So if you take acetic acid, for example here, 0.1 mole of acetic acid, and its conjugate base here, sodium acetate, and mix it in water, you have a buffer, and that buffer is called a acetic acid acetate buffer, or an acetate buffer. So let's see the importance of that. So here we have acetic acid and its salt, the acid anion, so that's the buffer. Let's see how it works. If you should add a strong acid to this buffer here, the strong acid, of course you know a strong acid is H plus or H3O plus, will react with the conjugate base here to form more acetic acid, and of course, as you know, acetic acid is weak. so the pH does not change a whole lot. Let's see how it works on the opposite end. If you should add a strong base, the strong base here is OH minus. It will react with the acetic acid and give you the acetate anion, which is shown here, which is a conjugate base of a weak acid. So therefore the pH will not change as much as adding just your strong OH negative. So once again, a buffer is a solution that's resistant to changes by adding an acid or a base. So as we mentioned earlier, a buffer is made by mixing a weak acid, which is salt. The pKa of a weak acid you can tell from the pKa calculations or from that table. So you may be wondering, how do we create buffers that can buffer at different pHs? Of course, as you know, you can buffer at a pH of 4, or you can buffer at a pH higher than 4 at 9, for example. So let's say you have a solution that you want to have buffered at 9. So what you do is you get an acid that has a pKa around 9. The acid that does that is boric acid, and it's salt. So you mix the acid and the salt equal concentration. You have a buffer that will buffer at pH 9.4. So after making that solution at 9.4, making that solution, if you add an acid to it, the pH will not change a whole lot from 9.4. The pH will decrease, only slightly though, but it will be in the region of 9.14. If you add a base to it, the pH will increase only slightly, but it will remain in the region of 9.14. So here's just added information for you. Henderson Hasselbalch, they, of course, as a team, discovered an equation that you can use to determine what type system you need to buffer at a particular pH. So if you need a pH to be a buffer system to pH to buffer at 9.14, you get an acid that has a pKa of 9.14. So that's the Henderson-Hasselbalch equation. Just remember that name. We won't be using it in this course. So lastly, let us look here at another practical application. We know the pH of human blood is 7.4. And of course, as you know, you don't want that pH to change a whole lot. So whenever you ingest or get in your system an acidic solution or a very basic solution, you want that pH to be constant in that region. How is that maintained? That pH, of course, is maintained by 3 buffers in the body: the carbonate, the phosphate, and proteins. Of course, as you can imagine, the body is very complex. So that's why the buffering system here is a little more complex than the ones that you will see in the lab. So once again, this is the end of that chapter. So once again, what you need to remember from this chapter is that it's possible to have buffers, and the buffer is used to maintain the pH in the region of the buffer. So after adding an acid to a buffer, the pH will change, but only slightly. It will decrease because it's an acid, but only slightly, but remain in the region of the buffer. If you add a base, the pH will increase, but only slightly, but remain in the region of the buffer capacity. So that's an important concept in chemistry. So once again, this is the end of chapter 8. We have an exam on Thursday, which will include chapter 8 or emphasize chapter 8, but it will include chapters 6, 7, and 8. But I will send out here and my usual reminders and announcement so you can get ready for the exam. So continue to study hard. Remember, take your time and go through this chapter here. You'll need your calculators and you'll need your periodic table, so make sure you can do the calculations and continue to read the text and study hard. So get ready for your exam on Thursday. Okay? Bye.